because I record everything in Zoom, well, we'll talk about that with the syllabus, but I'm recording everything in Zoom and all that kind of stuff to you guys' benefit. All right, so let's pull up the syllabus that I've made here. So I have the 6 different classes listed with the 2 different class names because somehow that happened. This is both micro and nano electromechanical systems and also microsystems principles. I don't know why they don't have the same name. That was not up to me. I am Dr. Hartman. My office is all the way at the other end of the hall, room 211. My office hours are Tuesday through Friday, 2 to 4:30 p.m. Howdy, Stephen. My email address is mylastname@latech.edu. And my office phone number is listed there. Don't call me, just email me or come drop by. I'm not in there enough to make that a worthwhile thing. In the event of, I don't know, weather emergency or COVID-23 or something weird, we'll handle the class on Zoom. Our objectives for this class is to study really 3 different classical MEMS devices: the accelerometer, the pressure sensor, and the gyroscope, and use those 3 examples of classical MEMS devices to go into detail the different types of sensing and actuation schemes that are used. And then once we cover kind of the meat and potatoes of MEMS, we will dive deeper into newer subset areas like optical MEMS, bio-MEMS, RF MEMS, and things like that. The textbook for this class is officially Practical MEMS by Dr. Vili Kajikari, who was my original PhD advisor. I have been told by the bookstore that that book is no longer in print. You don't actually need a book because I'm going to post all of my lectures and all that kind of stuff online. So you can certainly, I don't know, buy a used copy off of Amazon. I don't think Vili will get the money from it, but he'd be tickled to find out that people are still buying his book. I've listed a couple of other reasonable textbooks that you could use, and I'll pull information from those and provide it to you. Disability disclosure stuff. If you need testing or classroom accommodations, let me know as soon as possible. And then I provide the phone number and the email address or the link for ODS. Attendance. So this is what I was talking about with Zoom stuff. The official attendance policy for this class is that that's found in the university catalog. Effectively, since this is a 3-hour class, Monday, Wednesday, Friday, officially you all are allowed to skip as many as 3 class periods with impunity. Unofficially, you are all adults that are paying to be here. I get paid either way. So if you want to be here, that's great. If you don't want to be here and you want to handle everything over Zoom, I think it's a better experience if you're here personally, but that is your choice to make as an adult. Honor code stuff, effectively don't cheat. Academic misconduct stuff, continue to not cheat. Regarding the behavior, as long as you don't beat me up in the parking lot or act aggressively towards each other, we'll all be okay. Let's see, keep on scrolling down. Homework. So my goal is to assign 8 homework assignments, roughly 1 per week, but not any on the exam weeks and stuff like that. We'll see how that goes. For those of you that have had me in the past, the number is likely to be lower, but that's my goal, is 8 assignments. These assignments are meant to be worked individually. Please make sure that I can read them and all of that kind of good stuff. There will be a project associated with this class. It is a research project where you are going to write a literature review paper in IEEE format on a MEMS technology of your choosing. And so what I mean by that specifically is you could write a review paper on the current state of the art of RF MEMS or microfluidics or something like that. Or you could look at the current state of the art for a particular type of device. That's largely up to you. I would like for you to discuss your topic with me before you really get going on it, because I don't want you to put a bunch of work into something that I don't think is appropriate. And then at the end of the class, you will give a presentation on your topic of choice. These are going to be individual assignments. Actually, I might make it a group assignment for undergrads and an individual assignment for grad students. I'll flesh out those details hopefully by Monday. What? Yeah. Or as long as you're supposed to be here. Yes. All right. Exams. There's going to be 2 exams given during this class. Those of you who have had me before are pretty familiar with the way that I typically do exams. So there's going to be an in-class portion that's worth half of your exam score, and a take-home or out-of-class portion that's worth the other half. No makeup exams will be permitted unless you let me know why you can't show up for the test and all that kind of stuff to begin with. Each of the different things in this class, homework, project, and the 2 exams, are all worth 25% of your grade. I need to edit that because in-class assignments and mini labs are not part of this class, so that was me copying stuff over from my circuit syllabus apparently. So I'll have to fix that. The grading scale is a traditional 10-point scale. I am a jerk and do not curve or round grades up. So if you want to make an A in my course, you need a 90 or higher. This contents of the syllabus are not expected to change, except I'm going to fix this typo talking about things that do not occur in this class, because that's completely asinine. I reserve the right to change the syllabus if I need to, and I will let you know if and when those changes are made. Here's a little bit regarding the emergency notification system. Effectively sign up for this so that if we have a snow day, you get a text and don't show up to school when nobody else does. Scroll the wrong direction. And then we have our COVID-19 policy, which has gone from like 6 paragraphs to 2. Short answer is, if you feel sick, don't come to class and get me sick, or I'm going to get real pissed off. We have Zoom and all that kind of stuff for a reason. I cannot emphasize how mad I will be if you get me ill. So don't do it. And then some stuff about counseling services, how to access them and all that kind of good stuff. And then we have our tentative course schedule. So today, in the next 5 minutes or so, I will stop ranting about the syllabus material and start ranting about the lecture that I've prepared. Then we're going to go through a review, very brief review of microfabrication processes. This is largely what you should have learned in your MSE 501 class, but because so many of you didn't take it somehow, I'm going to talk about it here because it's useful. Beginning of next week, we're going to start reviewing electrical and mechanical concepts. So this will be a crash course in electronic circuits and statics as applied to this class. So for you EE students, you're going to need to pay attention for the statics part. For you guys who have a strong background in ME, you're going to have to pay attention to the electronic circuits part. And for people who don't have a background in either, it's largely going to be new material. Then we'll actually start addressing things specific to micro and nanoscale systems like noise, and then get into our classical devices and all of that kind of good stuff. I hate the winter quarter with a passion, just as a kind of off-topic thing. All these breaks and stuff like that make me absolutely miserable. So I've tried to make things as not awful as possible. So our first exam will occur effectively 2 weeks after we get back from the break, so that you guys have had time to get your brains used to doing things again. And our final exam occurs before we get out for Mardi Gras break, so that, I don't know, a 3-day hangover won't completely kill your grade when you come back and all that kind of good stuff. So I'm going to try to stick to that exam schedule as best as we can. After our final exam will be when we do the student presentations and all that kind of good stuff. So really no new material after we hit kind of the middle of February. I do have one date that says to be determined because I kind of ran out of topics that I wanted to cover. So that might be a review day. It might be a catch-up day. We'll see when we get there. So, but this is the pace that I intend to set. All right. Does anybody have any questions regarding the syllabus? Good deal. All right. So I have prepared a brief actually I should take roll. That's the thing that I'm required to do as part of my job. Let me get this PowerPoint up and then we will. All right. So one thing that I want to point out here, this is my first time teaching this class since before I was a doctorate. Like I used to teach this class for my PhD advisor many years ago. I am in the process of updating all of my notes and all of that kind of good stuff. Back in the day, I did everything on PowerPoints. I'm going to try to continue to do that for this class. So hopefully I will find the time to make new PowerPoints for everything. So just kind of bear with me as I'm restructuring this class because I haven't taught it in forever. So, all right, roll stuff. So I see Sam and Hayden. I saw Mr. Gordon come in. You're Timothy. All right, I know Jonathan from Circuits 1. All right, oh, and Leslie, you're taking this class as 451, right?
Yes. Also, I have to talk to the register. It's still not on my box.
It's there. The registrar isn't going to add you to it. Like I filled out the form.
Yeah, it's still not on my box because I tried paying for the class yesterday and it's still not on there.
Did you add it?
I should have.
You should be able to add it on Boss now that the permits and all that kind of stuff have happened.
It was like it was right at the.
I used to think that they added it for me, but at some point,
For a while.
either that
I think it
changed.
did before because I used to not have to, and then I think I did 1 year.
I did it last quarter for.
So when I looked at your petition yesterday after I had signed it, it said it got approved. It said authorized add-on Boss, which means you're responsible. So until you put yourself in the class, you're not getting put in the class. They used to add you to it, but they don't anymore for whatever reason. All right. I'm going to pre-apologize for just horrifyingly messing up most of these names. Rohit Bodu, was that remotely correct? Tell me if I'm wrong. Good. Okay, Rohit Bodu. Aniruddha Chowdhury. How bad did I screw that up?
That's fine.
That's right. You're like, these dumb white people are just going to continue to mess it up. Just let them do it. Sounds great. Prova Joy. All right. Did I feel like I got the joy right? Not sure about the other bit. Okay. Madi Rudbari. All right. Kritik Saxena. All right. Jack Weir is not here because I know who that is. Chengong Gong. Okay, so who are you? Okay, actually, so let's start this. Which class are you enrolled in? MSE 502. Okay, so let's go back. All right. I'm going to ask you to write your name down. It's at the bottom, yeah. So that we don't spend 45 minutes of me trying to figure out.
Are you missing a section?
There is.
So you got 5 pieces of paper.
There's nobody enrolled in this 657 section currently, so I didn't print out a blank sheet of paper. But it looks like I need to add at least 2 people to the 402 page after we get out of here. Okay. So course administration type stuff completed, lecture type stuff going. And this today's lecture will not take the whole time because it's just a brief background and all that kind of stuff. All right, so this is what we're going to be talking about today. And let me move this Zoom thing out of my way so that I can see what the hell it is I'm talking about. And I want to turn off whatever this thing that says subtitles is. Okay, because I don't need that. So we're going to talk about an overview of MEM, a very brief history of MEMS devices, and then a couple of MEMS applications, and call it a day. So let's talk about what MEMS are. MEMS are micro electromechanical systems. This phrase was actually coined in, I believe it was 1986, by a request for a proposal, an RFP, by the United States government agency, DARPA. Okay, so MEMS, or micro electromechanical systems, are a miniaturized device or system that contain both electrical and mechanical components, and it is characterized by its small size. So for a MEMS device, we're typically talking minimum feature sizes on the order of ones of microns all the way up to hundreds of microns or micrometers. Anything smaller than that would be considered a NEMs, or nano electromechanical system, and anything larger than that is typically considered a macroscopic system. Okay, many MEMS devices are scaled down versions of macroscopic designs, meaning most of the classical MEMS devices, like accelerometers, gyroscopes, and pressure sensors, were invented literally in the 1800s, large-scale systems. Where MEMS came in was trying to figure out how to make those devices significantly smaller so that they could become more ubiquitous. Prior to the development of MEMS, the proof mass on an accelerometer was usually on the order of a few kilograms. So they were very large devices, several inches in scale. They were extremely costly and did not get a lot of applications. And then in, I think, the early 1990s, when the first commercial MEMS accelerometers came out, the proof masses, instead of being on the size of kilograms, or actually on the size of, in the textbook that officially we use in this class, and this is one of the things that my old professor annoyed the hell out of me with, nanokilograms or micrograms. So very, very small proof masses, very, very small physical structures of springs and all of that kind of stuff. Because they're so small and because they're made using standard CMOS processes, they can be manufactured extremely cheaply. And so the application or the utilization of these devices has gone from, tens of thousands to hundreds of thousands of units to literally millions, if not billions of units of these devices due to the miniaturization. Okay. That being said, the development of microfabrication processes that came along with the IC industry and the MEMS industry has also led to the development of completely new designs as well. So it's not all just shrinking down macro scale things. New technologies have emerged because of the research in this field. MEMS are used everywhere. How many of you have a cell phone in your pocket or on your person? Everyone. Steven's got two because he jokingly deals drugs outside of school. So, yeah, please don't get me fired. So every one of us has a cell phone, which means every one of us has probably 15 plus MEMS in our pocket due to the accelerometers, gyroscopes, resonators, and things like that that are used as part of the cameras, microphones, radios, and all of those kind of constituent parts of a cell phone. Okay. Since MEMS were created, their utilization has drifted from strictly research into large-scale industrial applications, and now we are in a place where consumer application of MEMS is extraordinarily prevalent. So let's talk about the history of MEMS. Okay. Without the discovery or invention of the integrated circuit, MEMS technology would not exist in the form that it does today. Okay, so critical elements in the development of microsensors and MEMS, like the anisotropic etching properties of silicon or the discovery of piezoresistivity in silicon. These were discovered during the research that established the IC industry. Really, discoveries in the IC industry happen about 10 years before they get integrated into micro scale devices like MEMS, okay? So the first MEMS device is the resonant gate transistor, and it was invented by an engineer at Westinghouse, okay? So if you hear the word transistor, you will likely think that this is actually an electronic device, not a MEMS device. The reason why this is an electronic device, and of course I can't have a mouse here, so I'm going to get up and point at stuff, is because of this cantilever beam right here, okay? So in a traditional transistor, like your MOSFET device, because that's what this would be compared to, the gate electrode physically sits on top of the oxide layer, and it is at a fixed distance away from where the channel is established. With the resonant gate transistor, instead, we have a very primitive example of electrostatic actuation. So we have this attachment point to our substrate here, and then we have this cantilever beam. If we apply a voltage here and a polarization voltage here, we have two different potentials on our gate and on this plate right here. And what's going to happen is this cantilever beam will become attracted to this input force plate down here. As the cantilever beam becomes attracted to it, it will physically deflect down, right? And that in turn changes the distance at which the gate electrode is oriented physically above the channel, which is changing the threshold voltage of the device and changing its on-off characteristics. So this is the first true example of a MEMS device because it includes a mechanical component, the electrostatic actuation of this gate terminal to an electronic device. So it is an integration of statics and circuits, which is all true MEMS really are, right? In the 70s, IBM established a micro machining research group led by a gentleman named Kurt Peterson. Do yourselves a favor and look this guy up. He is bananas, insane inventor. Okay, like he is absolutely phenomenal. He's got, I think it's only something like 37 patents, but he's been CTO for multiple different companies and all of this kind of stuff. Like it's got to be probably one of the richest people you don't know their names because of the amount of life-changing inventions that he has dealt with. So he developed MEMS pressure sensors first, and then he and IBM developed effectively the inkjet printer head, which utilizes MEMS to put ink to paper, rivaling the efficacy of laser printers and all of that kind of stuff. In fact, modern inkjet printers can almost produce photorealistic images, okay? So this is an interesting MEMS device for a couple of different reasons. We can see a schematic diagram here on the left, and then a little SEM image of the printer nozzle itself. So this device uses piezoelectric actuation. Who knows what piezoelectric crystals are? Anybody got any thoughts about a piezoelectric crystal? So piezo is a Greek word which I believe means to squeeze. And so a piezoelectric crystal is an electromechanical transducer. So what that means is that it converts mechanical energy into electrical energy or electrical energy into mechanical energy. So for this particular device, if you apply a voltage across the piezoelectric crystal, depending on the polarity of that voltage, the crystal will either expand slightly or shrink slightly. So for this particular device, you would apply a voltage across the piezoelectric crystal, which would cause it to expand. The expansion of that piezoelectric crystal will cause this diaphragm to deflect downward, putting pressure on the ink cavity, which squeezes the drop of ink out of this needle effectively, right? So that's how you squirt ink out. When the piezoelectric crystal has an opposite polarity voltage, it shrinks, causing a small amount of vacuum pressure to suck more ink into the cavity, and that cycles over and over again. So you have this membrane deflecting down to push ink out, deflecting up to suck ink in through the reservoir, and then it's spitting out little ink droplets all over the paper. Modern inkjet printers don't use this piezoelectric crystal actuation method because it consumes far too much energy effectively. Instead, they actually use a process called thermal actuation, where you heat up ink in the cavity, and then it causes these bubbles to form. The bubbles push ink out, and when the bubbles explode, that creates the vacuum pressure, which draws ink in from the reservoir, and then that process repeats over and over and over again. So anyway, so these are some of the earliest MEMS devices. In the late 80s, so actually let me stop here. This particular device, the inkjet print head that's shown here, is developed by a bulk micromachining process. So a bulk micromachining process, which we're going to talk about in much greater detail on Friday, effectively means you are taking a large silicon substrate and performing processing steps on it specifically, right? So that's how most pressure sensors and things like that are made, where a pressure sensor is simply just a diaphragm that can deflect, and you can measure that deflection. That's actually what this is based off of. The devices that we're about to talk about here, some small scale micro motors, were made using surface micromachining techniques. Okay, so that's a different MEMS development techniques, where instead of etching large portions of crystal, you build microstructures on top of your substrate. So this is surface micromachining, is very, very compatible with modern CMOS processes, which is why the overwhelming majority of modern MEMS utilize this. Okay, so in the late 1980s, surface micromachining became the next big thing in MEMS, leading to the creation of microscale springs, gears, and cranks. And in 1989, researchers at UC Berkeley developed micromotors. So these guys work on the principle of electrostatic actuation, much like we saw with that little cantilever a while ago. So we have a three-phase drive system here on this picture on the left. And effectively what happens is we apply a voltage here, and we apply a voltage to our rotor. And what's going to happen is that application of voltage is going to create a torque. It is going to turn this rotor in order to maximize the capacitance seen between this surface and this surface. We can see up here, this surface and this surface of the gear are slightly out of phase. So when we turn this voltage off and turn this voltage on, it's going to wind up pulling this portion of the rotor to make it completely in phase, and that bit cycles over and over and over again, and that's how we get rotation in a micromotor like this. For this particular design, the rotor was about 120 microns in diameter, so a very small amount of mass to cause to spin. Guess how much voltage it took to get it to actuate correctly? But this is a wild guess because you guys don't know any of the math involved. Just take a random guess. A little higher.
A whole volt.
350. 350 volts.
I was thinking it'd be maybe double digits.
Yeah, 350 volts in order to cause this guy to spin. Okay,
They got kind of bold in their testing, didn't
they did indeed, right. So as we've made more advances in how these things work and the modified processes, micromotors have definitely stepped down. It took 350, three-phase, 350 volts in order to get this thing to spin at 500 RPM. Okay, that's a lot of energy going into this thing. Modern processes have made our micromotors and things like that much, much more efficient, but the technology emerged really in the late 1980s. Okay. All right. So up until this point, there were a few commercial applications of MEMS, but largely it was just research of what can we do? How can we make things smaller? You can find pictures of very silly MEMS electric guitars that are played with atomic force microscope tips as their plectrum effectively, and just weird and dumb zany ideas that don't really have a lot of practical application. But as we moved out of the 1980s, we hit the 1990s, and this is where government agencies start getting involved. And we saw an incredible amount of funding go into this area. In fact, this funding was so much that Louisiana Tech University was able to build and construct the Institute for Micromanufacturing. Back in the early to mid 1990s, it was literally a world-class institution. For those of you that have been there recently, you know what's going on. So anyway, so in the early 90s, MEMS research exploded because largely the United States Department of Defense dumped a ton of money into miniaturizing technology, okay? At about this same time, two large industries started putting a lot of money into MEMS as well. They were the automotive industry and the entertainment industry, okay? So on the left here, this is a analog devices ADXL accelerometer. Let me turn off the lights here so you can see this picture. So I believe this is a single axis accelerometer. So in the middle here, we have our proof mass. Okay, so an accelerometer is a simple second order harmonic oscillator containing a mass, a spring, and a damper. Okay, so we have this large proof mass in the middle. We have springs here on this side and a set of springs over here on this side, where these springs are literally nothing more than silicon beams, which are able to deflect in pretty much a single direction because of the orientation of things. And then all of this stuff on either side of the proof mass is a ton of parallel plate capacitors. And so depending on how that proof mass moved, or the amount of deflection of these springs, it would cause a change in capacitance, and measuring that change in capacitance told you what the change in acceleration was. Okay, so that's how a basic capacitive accelerometer works. Anybody have any idea why there are tons of little holes in the proof mass? So air at the micro scale is a viscous fluid. So if you didn't have all of these little holes to allow air to escape, you wouldn't be able to get a large amount of movement out of your proof mass. We'll talk about air damping and all that kind of stuff at a later date, but you'll see in a lot of these designs, they have little bitty holes featured all over the place, and it is literally to allow air to escape more easily, because you can create a bubble that will ruin your entire device. Over here on the right-hand side, this is a very rudimentary depiction of a micro mirror array that was designed by Texas Instruments. This is called the digital micro mirror device, or DMD, and it is the flagship part of their DLP series of projectors, which are still in use at movie theaters and in homes around the world. There very well may be a DLP chip inside of that projector right there. So these TI micro mirror devices are really super neat because it is an integration of a mechanical device, the mirror array and all that kind of stuff. It utilizes electrostatic actuation to deflect the mirror positive 12 degrees and negative 12 degrees, and it sits on top of a CMOS memory cell. Okay. Each individual mirror has its own memory cell associated with it. If the memory cell has a 1 in it, the micro mirror is deflected positive 12 degrees, causing light to reflect off of it. If the memory cell contains a 0 or digital 0, the micro mirror is deflected 12 degrees in the other direction, effectively scattering light. So each one of these mirrors is a pixel. They're tens of microns in dimension, so you can put millions and millions of mirrors in a very, very small chip, and that's how you get high scale resolution for your movie projectors and all that kind of good stuff. These were first commercialized in the mid 1990s, and we're still using them 30 years later today. So huge, huge advancement in the field of MEMS.
They're also using those in laser photolithography 3D printing now.
Cool.
Those are becoming a lot cheaper. They went down from about $700 for a 3D printer using this technology to about $400 to $500.
That's awesome. I did not know that.
Get really high resolution because the alternative is LCD.
Right. All right. So as the field of MEMS became more established, multiple different branches of MEMS grew. Optical MEMS, bio-MEMS, microfluidics, RF MEMS, and NEMs all effectively hit their infancy in the mid to late 1990s, and we're going to talk about all of those areas in more detail later on. And then once we hit the 2000s, that's where the switch from industrial application to consumer applications came about. Okay, we as consumers deal with MEMS constantly. Like I said earlier, there's probably between 15 to 30 MEMS in every one of our cell phones, depending on the model that we have. MEMS are in my fancy pants watch here. They're in our video game systems. They're in our Wi-Fi routers. They are all over the place. Our modern quality of life would not exist without the proliferation of MEMS systems. All right, so now we're going to wrap things up here by talking about kind of the different types of MEMS that we're going to discuss in this class. So we're largely going to focus on our general purpose MEMS, which can largely be put into two different groups. Well, actually, there should be a third one here, which would be pressure sensors, but we'll talk about that later. Inertial measurement units. So this is accelerometers, gyroscopes, and magnetometers. And then touch screens are used in a wide variety of industries. So the picture on the top left is a 3-axis gyroscope, so it can measure pitch, roll, and yaw. So this one in particular actually was developed for the iPhone 4, which was the iPhone that was in use while I was in grad school. I got paid to blow them up by the US government. It was pretty neat. So modern IMUs in cell phones, so this is a 3 degree of freedom because it can determine controlling yaw. Modern IMUs are 6, so they incorporate a 3-axis accelerometer and a 3-axis gyroscope, so you can determine displacement in the X, Y, and Z directions, as well as pitch, roll, and yaw, all in one single chip. The picture on the bottom is I think this is from the mid 2000s, an example of a capacitive touchscreen element. So effectively, you have that bridge in the middle, that thin region of silicon, and if you touch near it, it causes it to deflect down. That deflection of that bridge area over a ground plane causes a change in capacitance, and that change in capacitance can then be sensed, which tells you where you've touched the screen, letting you know to do certain things. Okay? And we'll talk about all that kind of good stuff in this class. Optical MEMS are just MEMS devices which control light on small scales, so can make micro lenses, diffraction gratings, mirrors, interferometric filters, phase modulators. They're used in displays, optics, spectrum analyzers, and routers. On the right-hand side of this slide, we have a picture of a Fresnel lens. Excuse me, I almost mispronounced it. So a Fresnel lens is used in either the collection or collimation of light. So effectively, if you have a standard lens, it's going to have a very wide thickness in order to make all of the light have a common focal length. The Fresnel lens can accomplish that using a much thinner lens by having all of these concentric ridges, which effectively, if you put collimated light in, it focuses all of those light rays to a common focal length. If you put uncollimated light in, it effectively puts all of the light in parallel. So wide variety of applications, especially in laser electronics and things like that. Then we have BioMEMS, micro cantilever sensors that deflect depending on the size of the molecules that affix to them. Biometric sensors, micro needle arrays, so that when you inject medicine into somebody, it doesn't actually go into the subdermis and hit your neurons and things like that, hit your nerves, so you can inject medicine without causing any pain. Implantable microelectrodes. I am a diabetic, so I actually use these MEMS based test strips every single day. They're used in medical imaging. The picture on the right-hand side here, hopefully none of you guys are old enough to have gone through a colonoscopy or anything like that just yet, but effectively this is a pill containing multiple MEMS devices, cameras, and things like that you swallow, and as your body processes it through your GI tract, it takes pictures of everything, and then it transmits all those pictures out to a receiver, and you just pass it in your stool when you're done with it. So it takes a picture of your full tract, again, MEMS based. Microfluidics, which a couple of you guys mentioned that you were dealing with for part of your PhDs or graduate studies. There's also a region of MEMS. Microfluidics very basically is any device that contains chambers and tunnels where microfluids flow. So this was development of microchannels, lab on a chip or system on a chip, and MUTAS systems. Without microfluidics, we couldn't do COVID detection. Like almost all of the COVID tests that were done in the last couple of years were based on PCR process, polymerase chain reaction. Polymerase chain reaction tests are literally a direct application of the use of microchannels, where you have a series of microchannels and reservoirs with a temperature gradient across them, and as your sample goes through each cycle, so from the cold side through a chamber to the warm side, DNA replicates and amplifies over and over and over again as it goes through this hot-cold cycle. This is what has revolutionized DNA examination for the criminal justice system and all of that kind of stuff as well, how we can use incredibly small samples of DNA to determine, you know, who this particular sample belongs to. So microfluidics is a huge, huge aspect of MEMS. This is a little self-aggrandizing or promotion here. The picture on this slide is actually from my PhD dissertation. I made a microfluidic variable capacitor for NASA using a process called xerography. So my limited research in this area was actually in microfluidics as well. Then we have RF MEMS. This is one of my favorite, maybe it's weird to have a favorite MEMS device, but this is one of mine. The picture shown here is a variable capacitor that uses a capacitive comb sensing mechanism and a torsional spring actuator. So the reason why this is one of my favorite MEMS devices is because back in my graduate research lab, we had an old Russian variable capacitor. And effectively, this was a device about the size of a football, really. I mean, it was pretty large, and it had a series of plates that were fixed and a series of plates that could move as you rotated this thing. And so how it worked was you tuned the area of the capacitors. So if you rotated the device so that the plates were in phase, you got a larger capacitance. If you rotated so where the plates were out of phase, you got a smaller capacitance. Well, this is the same exact principle, but on the micro scale. Effectively, you have a bunch of fingers like this, and then you have another set of fingers, and it can rotate up and down, changing the area of overlap and thereby changing the capacitance. So to me, it was really neat to see something, this old school late 1980s Russian technology transformed into the micro scale during the time that I was working on these type of devices. Okay. RF MEMS range from micro resonators and relays, tunable capacitors, antennas, inductors, and they are used in all modern communication systems effectively. And then lastly, we get into NEMs, which I know the least about, so I'm trying to brush up on my my work here. The NEMs device that I'm probably the most familiar with is the FinFET. I consider that to be a NEMs device instead of just an nanoscale electronic device, because the physical structure plays such an important role in the device operation. In a FinFET, effectively, your gate, instead of being your gate outside, instead of being a simple planar surface, is actually a three-dimensional surface that wraps around your source and drain regions, and then your gate electrode is deposited on top. So anyway, so that is our introduction to MEMS and kind of talking about where we're going to be going with this class. All of the images in here, here are your references for all that kind of stuff if you want to look at any papers based on any of this technology. And I'm done ranting for the day. So unless anybody has any questions, I will see you guys on Friday where we're talking about microfabrication processes.